So let's say we want to find the domain of this function. F of xy equal to 1 over the square root of x plus the square root of 36 minus x squared minus y squared. Oh, I should make sure the microphone's on. Yeah, it's on. All right, cool. So the thing about these domain questions is the usual kind of domain rules still apply, meaning we can't divide by 0, we can't take a square root of a negative, we can't take a logarithm of a 0 or a negative. So when I see a square root, I automatically think, all right, all the stuff inside the square root better be greater than or equal to 0. So I know that this part here is going to lead to saying this. In a similar way, this part here, I have a square root of x, so I have to say 1, that the inside of the square root is greater than or equal to 0, but also I can see that since that's in the denominator, I don't actually want 0. Because if x was equal to 0, the square root of 0 is 0, and 1 divided by 0 is undefined. So what I really get from here is just that x has to be greater than 0. And the thing about domains of multivariable functions, like functions of 2 variables, is we're talking about a region in the xy plane. Right? We're trying to say like what points in the xy plane are in the domain of this function. I'm trying to make sure. Okay, yeah. So x greater than 0. I'm gonna draw this with the knowledge I have already what I did. So usually I would draw the xy axis like regular lines, but since I don't actually want to include where x is equal to 0, which is the y-axis, I'm going to draw that as a dashed line. So I'm going to draw the x-axis solid, the y-axis as a dashed line. So I know that's like the end of one of my boundaries. So for x greater than 0, I'm going to want everything on the right side of the plane. So this is going to give me the right side of the entire plane, which I'm not actually going to shade in, right? I could shade all of this in, but we're going to be limited also by this. So we should kind of hold our horses. A lot of the times with these domain questions, you're going to see an x squared plus y squared or a minus x squared minus y squared. If you see one of those things, you kind of want to isolate it. So I would rewrite this inequality as 36 bigger than or equal to x squared plus y squared.
This is right side of
entire plane.
Okay.
Yeah. So it's true that x squared plus y squared equal to 36 is the equation of what kind of graph?
It's a circle.
Right. It's a circle centered at the origin with a radius of what?
6.
Exactly. Right. So what we're going to do is we're going to draw. No, so this equation is kind of the border between what we want and what we don't want, because we want x squared plus y squared to be less than or equal to 36. And I know I was watching his lecture from class the other day. He just kind of said we want this side of the parabola, and I feel like didn't really explain how we know we want that side. So there's an easy way to figure it out. Let's draw this circle first, though. So let's say that's 6. And then we'll just do it like that. All right, that's an all right circle. Okay, so this point here, I'm drawing it open because I know I don't want it. Because again, I don't want where x is equal to 0. Same deal there. And that point there would be -6. Okay, so the question is, which side of this border do I want? Do I want everything inside the circle or everything outside the circle?
I think you want in the circle.
Yeah, but how do you know for sure? There's an easy way to check. Test any point you want. So test the origin. If I plug in 0, 0 into this inequality, is it true, or this, either way you want to write it, is it true that 36 minus 0 is bigger than 0?
Yes.
Yeah, then that point's in the domain. And so since that point is in the domain, we want everything that's inside the circle, except we don't want anything on the left side, right? Because we already said we only want the right side. So we really want all of that. Everything that's in the circle on the right side of the plane. On the other hand, just as a contrast, you could have picked a point that wasn't in the circle. Like we could have picked 6, 6 and tested that instead. And if you plug in 6, 6, you get 36 minus 36 minus 36, which is negative 36, which isn't bigger than or equal to 0. Welcome. What's your name?
Lisa?
Lisa, welcome. I already said welcome, but welcome again. Here for Co-17C? Right on. Yes, I think I just added you today. Well, cool. We're just talking about some domain stuff right now. And at some point, it's not super urgent, but at some point you just scan these QR codes and sign up for class. So other questions about this particular problem? Okay. That's an excellent question. So it's kind of annoying the way you write the domain for these functions of multiple variables. So the way I would write the domain and the way that you should write the domain is it's the set of all coordinate pairs x, y, such that the things that need to be true are true, meaning such that x is greater than 0 and x squared plus y squared is less than or equal to 36. There isn't really like a nice formulaic way of writing. Like it's not like in 17a where it's like the domain is everything from like 0 to infinity, right? We don't have that luxury anymore. So we're kind of stuck with this less pretty looking answer. Yeah, good question. Lisa, questions about this? I know you just walked in, so we could definitely revisit the whole problem if you would like to. Okay. Cool. Right on. So are there other homework questions that are particularly troubling?
I think it was like the I think it's 62. Yeah.
Let's take a look. 60. Oh, yeah. Okay. From the set of points at which the function is continuous. Okay, that's a great question. Yeah, so I'm gonna pick a slightly different example, but we'll talk about. So this question is easier than it sounds. But let's look at this example. So let's say our function was the natural log of x squared plus y squared minus 9. And our question is, where is this continuous? The not very good answer to that question is most functions are continuous on their domains. Most functions that we're going to encounter, as long as they're defined, they're going to be continuous. There are some exceptions, but most of the time, that's going to be the case. So this function is continuous where it's defined. So we need to look at the domain here. Back to domain. So we've got x squared plus y squared minus 9 has to be strictly greater than 0. Because for logarithms, we can't take the log of 0 or a negative number. And so if I was trying to describe the set of points, they didn't ask me to draw it. I'm still probably going to draw it. But if I was just going to describe the points, it's really easy to describe the points once you know what you're restricted to. I'm going to say that my domain is the set of all points x comma y such that that's true. It's not very exciting, but it is correct. Alternatively, you might write this as x squared plus y squared bigger than 9. a lot of the time with these things, when you have an x squared plus y squared pop up, we kind of isolate that on one side of the inequality. If we were going to draw the domain, well, again, I'm always going to think about, instead of the inequality, I'm going to think about the equality, x squared plus y squared equal to 9. And that's what I'm going to graph. So x squared plus y squared equal to 9, that's a circle, radius 3. I'm not going to say the center is the origin because most of the time these things have the center as the origin. And since I know I don't actually want it to equal 9, right? I want it to be greater than 9. I'm going to draw it dashed so that I don't have that as part of my domain. So 1, 2, 3. Draw lots of circles in this class. Okay, so there is my border of my domain. And now we have to ask ourselves the question, do we want the insides or do we want the outsides? Well, let's pick the origin again. If I plug in 0 for x and 0 for y, is my inequality true? See, 0 plus 0 minus 9. It's not greater than 0. That's okay. It means that this point, though, isn't in the domain, which means this side of the circle, the insides of the circle, is not the domain. It's everything that's outside the circle. So here's our domain. It's everything out here. It's the entire plane minus that circle in the middle. I'm curious about this other question here. No, that's not a problem. So looking at this other question, just because I feel like the other one's a little bit different, I think it is worth exploring. Well, I'll look at something slightly different. Let's say we had f of xy equal to, sure, 3 to the x plus 2 to the y over 4 to the xy minus 1. So for this function, what kind of thing do we have to worry about making undefined? Do we have any square roots? No. Do we have any logarithms? No, but we do have potential division by 0. So where might we be dividing by 0? And when I say where, I mean what x, y coordinates would make us divide by 0. Well, I'm going to set the denominator equal to 0, right? Well, I'm going to isolate the 4 to the xy. And what kind of powers make an exponential thing equal to 1? 4 to what? Right, that has to be 0. So what we need is x times y equal to 0, which means either x is going to be 0 or y is going to be 0. So what are we excluding from the domain? Well, everything where x is 0 or y is 0. So our domain, I would draw the xy axes, except those are exactly the things I don't want. My domain would be everything except for the xy axes. Like that. Not that you have to draw it, but that's how we would draw the domain. If I was actually trying to try and write it, I guess I would write the set of x, y such that x is not 0 and y is not 0. Right, yeah. So the problem says determine the set of points at which the function is continuous. It doesn't ask me to draw, although it probably wouldn't hurt to draw it. I would probably encourage you to draw it. The other thing I want to talk about here, though, just briefly, is that what about another point? Like, how do we know, just for example, is this function, f of xy, continuous at some other point? Say, like, at the point, I don't know, 1, -2. Well, the way you check that is it feels like we're going to do the same work twice, really, because you have to answer the question, well, is the limit as x, y approaches 1, -2 of f of x, y, is that equal to f of 1, -2? And for the most part, as long as you don't have some weird undefined thing, the answer is going to be yes. Because if I'm trying to take this limit, most of the time what I'm going to do is just plug in the values and see if I get a real number, which is the same thing that's going to happen when I find the function value. So kind of running out of room here, but what I'm trying to say is the limit as x, y approaches 1, -2 of this function, 3 to the x plus 2 to the y over 4 to the x, y minus 1. I'm just going to plug in 1 and 2, and I'm going to get something real. I'm going to get 3 to the 1 plus 2 to the -2 over 4 to the 1 times -2 minus 1. It's not pretty, but it's certainly defined, right? It's some gross fraction. And I think we can all probably agree that's definitely what f of 1, -2 is. Because unless there's some weird undefined thing, you're not going to have problems. Something that would be more of an issue would be something like, where'd that problem go? I had one. Oh, I need to answer this. Sorry, just one second. Apologies. Hello? This is he. Yes. Oh no. I'm sorry to hear that. Okay. Okay. That's okay, I understand. I do need to go because I'm teaching a class right now, but thank you for the call. I appreciate it. Okay. Sorry about that. Someone's coming to install something in my house and I need to it's not going to happen today because someone got in an accident. They're okay. I was like, oh no, that's too bad. So they're going to call back on Monday, probably during class time again. Yeah. Anyway, back to the math. So I'll edit that part out later. Yeah, most functions continuous where they're defined in this context. Oh, I was looking for my example of something that wasn't. Yeah, so something like this. If your function is, say, what do I got here? Where'd you go? F of x, y equal to y squared times sine squared of x over y squared plus 2x squared. This function, I will point out, is similar to the function in problem 58. This function definitely is not defined at 0, 0. Right? If I plug in 0, 0, I'm going to get 0 times 0 over 0 plus 0. And 0 over 0 is undefined, specifically indeterminate, which means it can end up taking on any value. However, this limit as xy goes to 0, 0 of this function, this limit actually does exist. It's a little hard. Oops, let's get that here. It's a little bit of a challenge to show it exists, but I think it's worth our while for just a second here. So to show this exists, I need to look at my notes so I don't forget how to do it. Because I was doing it the other day and I got things out of order. Make sure I do it the right way. Oh yeah, that's what we're going to do. So I don't think he'll focus too much on this in class, but he definitely this is a problem in your homework or similar to a problem in your homework. So there's a trick for something like this. And the trick is to notice the following. That y squared is definitely less than or equal to y squared plus 2x squared. It has to be true because 2x squared is definitely greater than or equal to 0 all the time. And then y squared divided by y squared plus 2x squared is less than or equal to y squared plus 2x squared divided by y squared plus 2x squared, also known as 1. So are you on board with me for that? Seem good? Okay. And then what we're going to do is we're going to say it's also certainly greater than or equal to, no, yeah, I should say greater than or equal to 0. It definitely can't be negative. It certainly could be 0. It certainly could be large, but it can't be negative. Well, it can't be that large, right? It's less than 1. So it's between 0 and 1. And now we're going to multiply the whole thing by sine squared. Sine squared also always non-negative, right? It can't be negative. It could be 0, but it can't be negative. The reason I point that out is because when you multiply inequalities by things, if you're multiplying by negative, you have to change the direction of the inequality. That's not an issue here, so we're not going to worry about it. So then I have 0 times sine squared is less than or equal to y squared times sine squared of x over y squared plus 2x squared is less than or equal to 1 times sine squared of x. And now we get to use the squeeze theorem. So it's definitely true that the limit as xy goes to 0, 0 of 0 is equal to 0. I'm just taking the limit of that. It's kind of boring, right? It's always 0, its limit is 0. It's also true that the limit as xy goes to 0, 0 of sine squared of x is equal to 0. Because as x goes to 0, sine goes to 0. And so since this thing is in between these two things, and both of those have a limit that's 0, it has to go to 0 as well. So then we can say by the squeeze theorem, or sandwich theorem, if you like to call it the sandwich theorem, we have to get the limit as xy goes to 0, 0 of this gross y squared sine squared of x over y squared plus 2x squared. That has to be 0 because it's between two things whose limits are both 0. So I let my wife know they're not coming today. Okay. You probably won't have to do too much of this. Like, I feel like this is something we don't typically focus on in this class a lot, but sometimes people talk about it. More often, you're going to be asked to evaluate limits like this where it doesn't exist. So as a contrasting example, we want to look at the limit as xy goes to 0, 0 of x squared times y to the 6th over x to the 5th plus y to the 10th. And so whenever you're trying to evaluate a limit like this, you want to start picking different paths. Because so really, if I didn't know this previous one was going to end up equaling 0, I would have been like, let's try y equals 0 or x equals 0 or y equals x or any path that goes through the origin. Y equals x squared, x equals y squared, y equals, right? There's literally thousands of choices. So that's what we're going to do here. We're going to start making choices. And I'll encourage you both that if you're ever doing problems like this, one of the choices you always should probably make is either picking x equal to 0 or y equal to 0, because it usually results in something being 0. So if I choose the path y equal to 0, then when I plug in y equals 0, my limit becomes the limit, well, y is already 0, so I don't need to write the y part. It's going to be the limit as x goes to 0 of x squared times 0 to the 6th over x to the 5th plus 0 to the 10th. Or simplified, it's the limit as x goes to 0 of 0 over x to the 5th. It's important that it's 0 over something that isn't 0 yet. Since x isn't 0, what's 0 divided by x to the 5th? What's 0 divided by 4? right? 0 divided by any non-zero number is always 0. So the idea here is that before we take the limit, we do the arithmetic, and 0 divided by something that isn't 0 is 0. And then the limit of 0, or the limit of a constant, is the constant. It feels almost like cheating, but it's not. It's totally valid. And then you might start trying other things. So the thing is, if we try x equal to 0, we're going to get the same result. We're going to get 0 over y to the 10th, which is going to go to 0. So we need to start trying other things. So let's try something that's probably not going to work. Let's try y equal to x. That definitely goes through the origin. So if I do that, you can replace the x's with y's or the y's with x's. It doesn't actually matter. I am partial to using x's if I have a choice. So I'm going to limit as x goes to 0 of x squared times x to the 6th over x to the 5th plus x to the 10th. And the way you can evaluate something like this without too much trouble is by factoring out the biggest power of x that you can. So I can factor out an x to the 5th from the bottom. So here's what's going to happen. You get the limit as x goes to 0 of x to the 8th over x to the 5th times 1 plus x to the 5th. I can cancel an x to the 5th. So that cancels. And here I'm going to be left with an x to the 3rd on top. But now look what happens. As x goes to 0, I get 0 over 1 plus 0, which is going to be 0 divided by 1, which is 0. Which isn't bad per se, but we're of the mind that this probably is a limit that doesn't exist, meaning we need to find a path that makes it so we get a different value. So the trick often with these problems is to try and pick some power of the other variable, like y equal to x squared or x equal to y squared, so that, how do I say this the right way? So that kind of all the powers even out to be the same thing. So this one, if you let x equal y squared, look what's going to happen. So if x equals y squared, which definitely goes to the origin, right? It's a valid path. I'm going to get the limit as y goes to 0 of y squared squared times y to the 6th over y squared to the 5th plus y to the 10th. In simplifying that, all of my terms are going to end up having the same power of y. I'm going to get the limit as y goes to 0 of y to the 4th times y to the 6th, which is y to the 10th, over y squared to the 5th, which is y to the 10th, plus another y to the 10th, giving me a 2y to the 10th. And then those y to the 10ths get to cancel. So I really just have the limit as y goes to 0 of 1/2, which is 1/2. And since those limits aren't the same, we can see that the limit doesn't exist. Different paths that give different values. So if I were to ask a test question about this, I would probably ask one more in this vein, where you're going to have to find different paths that give you different values. And I would imagine Dr. Didel would as well. Fun fact, I took a class from Dr. Didel when I was a student here over 20 years ago. He's been around a lot, as have I. He has also been around a long time. All right, were there any other, what time is it? Oh, we got plenty of time. Were there any other questions from the homework that were particularly challenging?
I think I have a problem with 36. I think it was mostly the negatives in the.
Sure. So draw a contour map of the function showing several level curves. Yeah, we should definitely talk about level curves. So level curves are not too terrible. Yeah, let me make it. Let's see. Yeah, let's look at this. So let's say we want to draw a contour map. I'm going to make it a little bit different. Of f of x, y equal to the square root of 16 minus x squared plus y squared. So what is a level curve? Well, I mean, it literally is a contour map. Like, I imagine you've both seen a contour map, like of the world where like the little lines mean you're at a higher or a lower elevation. So the idea is that we're going to pick the elevations and then we're going to figure out what the curve looks like. So this can be a long process or a short process, depending on how you do it. But let's kind of start off with some values. So we're going to pick, and this is where you have to kind of be fairly aware of what the range of the function is. So certainly this function couldn't have any negative values. Square roots only spit out positive values. It might be limited as to how large it can be. We'll see. So I'm going to pick kind of the easiest value I can think of. I'm going to pick a z value of 0. Or if you prefer, a function value of 0. But just like we use y equal to f of x, we're thinking of z equal to f of xy. So if I do that, here's what I get. I get the square root of 16 minus x squared plus y squared equal to 0. And now I would like to turn that into an equation that I can recognizably graph. So I'm going to square both sides. And then I'm going to move the x squared and the y squared to the other side, meaning I'm going to have that 16 equals x squared minus y squared. Now, you might not recognize this graph immediately. This is a hyperbola. And it looks kind of like this. I can see that if x is 4 or negative 4, y can be 0. Or really, I should say, if I let y equal 0, x can be 4 or negative 4. I don't get an x or I don't get the y intercept though, because if x is 0, there's no way negative y squared can ever equal 16. So we get x intercepts at 4 and negative 4. And then if x gets a little bigger, y can be a little bigger. So like if x were to be 5, y can be 3, which is kind of a fortunate choice. So here's what this thing looks like. And the same kind of thing on the other side. It should be symmetric. It's not quite the way I've drawn it. So here's the beginning of my contour map. I've let my C value, my level curve value equal 0. And now we're going to go higher up. So now we're going to let C equal 1 or Z equal 1. And I need more room probably. It's okay. So we'll do one more and then we'll talk about kind of the faster way to do this. So if we pick Z equal to 1, now we're going to get the square root of 16 minus x squared plus y squared equal to 1. We're going to square both sides. We get 16 minus x squared plus y squared equal to 1. And solving for x squared minus y squared, we're going to get x squared minus y squared equal to 15. So this is going to be just a little bit further in, right? Because now if y equals 0, we get x squared equal to 15. We get x equal to plus or minus the square root of 15, which is a little smaller than 4. So it would look something like this. And I often, when I'm drawing these things, like use different colors so it's easier to see like which line goes with which value to kind of differentiate them. And then we can keep doing this, right? We keep picking larger values for C. But here's kind of the better way to do this. The better way is to say, I'm going to pick C to be C. So let's say Z equals C. And so we want to graph the square root of 16 minus x squared plus y squared equal to C. So now we're going to solve for x squared minus y squared like we did before. So square both sides. And then 16 minus c squared is going to be x squared minus y squared. So we can kind of make a little table of c values and curves. When c is 0, we get x squared minus y squared equal to 16. When c is 1, we get x squared minus y squared equal to 15. When c is 2, we get x squared minus y squared equal to 16 minus 4 is 12. 3, x squared minus y squared equals 16 minus 9 is 7. X squared minus y squared equals 0. Oh, sorry, you can't see that. X squared minus y squared equal to 0 is kind of weird. So I'm going to try and draw this again just so it's not too terrible. I'm going to square root of 15 is really close to square root of 16. And then square root of 12 is about 3.5-ish, I think, 3.46. So we're like right there, kind of. And then finally, square root of 7 is like 2 point something. So here's kind of what your level curves would look like. I only drew the right side of them just because I didn't want to draw the other side of them. But I would label this as c equals 0, c equals 1, c equals 2, c equals 3. Oh, and then we should do c equals 4. So what about x squared minus y squared equals 0? Well, another way to write that is y squared equals x squared, which looks like either y equals x or y equals negative x. So my graph here has kind of gotten a little out of sorts because really the y equals x line shouldn't cross this. These should be a little bit more bent that way. So it should probably look actually, sorry. My math skills are good. My drawing skills are not always great. This should probably look a bit more like this, just to give you. So here's my y equals x. It's negative x. And this is going with c equal to 4. And then our other curves are going to look like this. There's c equal to 3. And there's c equal to 2. C equal to 1, and so on. So that's kind of, and again, I've only drawn the right side, right? The left side would also be there, a reflection of it. So the idea is that if you were to look at this kind of, if you took this and like thought of it sitting flat, you can kind of see that as you like, if I, for example, if I were standing here and kind of looking at my curve, right, it would go up kind of like this kind of inward hill kind of thing. And because as you move further inward, the C values, the height values get higher and higher and higher. There's something else I want to say about this. No, I guess not. On the other hand, if you were doing something like f of xy equal to the square root of 25 minus x squared minus y squared, again, I wouldn't do the thing where you just pick a bunch of different values. I would start with the square root of 25 minus x squared minus y squared equal to c, and then start working towards getting to an equation I know how to graph, meaning squaring both sides and then isolating the x squared plus y squared so that 25 minus c squared equals x squared plus y squared. So if I've got x squared plus y squared equal to 25 minus c squared, I know that my level curves are going to be what kind of shape? Well, if I've got x squared plus y squared equal to a number, I'm going to have a circle. With a center of 0, 0. And what's the radius of this circle going to be? I mean, obviously it depends on what c is, but as it's written, what would the radius of this circle be? You're close. That would be true if c was 0, the radius would be 5. But what if c was 1, what would the radius be? It's not a nice number. 24, because we're subtracting 1. But yeah, and if c was 2, it'd be the square root of 21. Or more generally, the radius is going to be the square root of that number, 25 minus c squared. So we can see that if c equals 0, the radius is going to be 5. And if c equals 1, the radius is going to be the square root of 24. And if c equals 2, the radius is going to be the square root of 21. And if c equals 3, the radius is going to be the square root of 16. If c equals 4, the radius is going to be the square root of 9. And if c equals 5, the radius is going to be 0, which is not exciting. But it is a point. So I should point out, if you have a circle with radius 0, you do have 1 point at the origin. So if I was going to try and graph this thing, I just got concentric circles, right? When c equals 0, my radius is 5. And then when c equals 1, my radius is just a little bit smaller. And then when c equals 2, my radius is still bigger than 4. I know my circles are not perfect. And then when c equals 3, my radius is 4. And when c equals 4, my radius is 3. And when c equals 5, my radius is 0. So I've kind of got like this mound, right? Or it's probably not a parabola actually. But I've got this thing that's like very wide circles at the base. And as you go inward, you get smaller and smaller circles. It's like a hill, right? That's the way I should say it. It's a hill. So you've got these circles are getting smaller and smaller and smaller as we go up and up and up. That's the idea of level curves, is you're just picking different heights and you're getting the shape of the contour at that height. All right. So let's use the last few minutes we have to start talking about, gosh, where'd you go? Partial derivatives. It's definitely partial derivatives. I mean, he talked about them a little bit in class yesterday. They're definitely, it's not, we're not done with partial derivatives. So partial derivatives. So when I think about a partial derivative, I really think about the fact that I'm essentially treating the variable that I'm not taking the derivative with respect to as a constant. So when we take partial derivatives, we treat the rest of the variables as constants. So let's look at some examples from 17a, some very straightforward examples. What if our function was cosine of x plus 6? What's the derivative going to be? Let's see, the derivative of cosine is a negative sine of x. And what's the derivative of 6? Right. So when you have a constant added or subtracted on all by itself, its derivative is 0. So constant by itself we get its derivative to be 0. On the other hand, if you have your constant multiplied by a function, then the derivative, well, the derivative 6 cosine x is going to be 6 times negative sine x, or we'd probably write it as negative 6 sine x. And what I like to say here is that when we have a constant multiple, it hangs out. It sticks around. It's not going anywhere. So constant multiples hang out. Constants on their own have a derivative that's 0. And that same idea is still going to apply whether your constant is 6 or whether your constant is y, because we're differentiating with respect to x. It takes a little bit of getting used to see like a variable and be like, oh, that's just a constant. But that's what we do. So let's look at some examples in these last 5 minutes here. So let's say we have f of xy equal to cosine of y plus x squared. We want to find first del f del x. That's what that curly d looking thing is. It's called del, D-E-L-L. If you write a d accidentally, no one's going to care. But it is a curlier looking d. So the derivative of this with respect to x is going to be 0 plus 2x, because the derivative of cosine of y, well, cosine of y is a constant as far as x is concerned. There are no x's in it. On the other hand, del f del y is going to be negative sine of y plus 0. Because again, as far as the variable y is concerned, x squared is a constant and its derivative is 0. Or we could look at the function g of xy equal to x cubed times tangent of y. So now if I take the partial of g with respect to x, I have x cubed times a constant. Constant multiples hang out. So the derivative of x cubed times the constant is going to be 3x squared times that constant. Or if we want to find del g del y, the partial of g with respect to y, now x cubed is treated like the constant multiple. So I have a multiple of tangent of y. That constant multiple hangs out. What's the derivative of tangent of y? Secant squared of y. Trig derivatives will definitely come back, so take a minute to review them if you have a chance. Wow, I just like squirted water everywhere. Really good. Hopefully I caught that on camera. We'll watch it later. So we got time. Yeah, we got time for one more example. It's it's a little bit long, but we'll do it. Oh, you got to accept class though. I should not hold you after. I should not hold you any longer. Oh, but it's close. So yeah, I won't hold you any longer than I need to though. So we'll start with this function, which is x to the 6 minus y to the 4th plus x cubed y to the 8th. And let's just look at some of the partials. So del f del x is going to be 6x to the 5th minus 0 plus 3x squared times y to the 8th. And I probably wouldn't actually write the 0. So I'm writing the 0 to really emphasize the fact that the derivative of y to the 4th there is 0. But in practice, you're not really going to write that. You're going to write 6x to the 5th plus 3x squared y to the 8th. And in a similar way, del f del y is going to be 0 minus 4y cubed plus x cubed times 8y to the 7th, or negative 4y cubed plus 8x cubed y to the 7th. A couple notational things here. This is one way of writing a partial derivative, but it's kind of a lot to write sometimes. So we do have an abbreviated notation. We write it as f sub x, and we say it as fx. So not f of x or f sub x, but we actually say just fx, and that means the partial derivative of f with respect to x. In a similar way, that's fy. And then we could also find the second partial derivatives. So del squared f del x squared, I'm just taking the derivative of the derivative again with respect to x. So it's del x of del f del x. So it's just the derivative of this with respect to x, which is going to be 30x to the fourth plus 6xy to the eighth. And notationally, we could call that fxx. And del squared f del y squared, I'm just taking the partial of this first derivative with respect to y again. So I'm going to get a negative 12y squared. And then 7 times 8 is 56. I'm going to get a plus of 56 x cubed y to the 6th. And we could call this fyy. Sorry, it's a little close there. All right. Last thing I want to say. There's two other second partial derivatives we like to talk about, which are the mixed partials. So they're del squared f del y del x and del squared f del x del y. So this one here says you do the derivative with respect to y of the derivative with respect to x, meaning you do x first, y second. So that's going to be del y of del f del x, which isn't too bad. The derivative of 6x to the fifth with respect to y is 0. The derivative of 3x squared y to the eighth with respect to y is going to be 3x squared times 8y to the seventh, which ends up being 24x squared y to the seventh. And what I want you to see is that it's the same either way you do it. Whether you do x first, then y, or you do y first, then x. I know if you read this from left to right, it looks like x is first, but when you apply derivatives, you read from right to left. So that would be the partial with respect to x of negative 4y cubed plus 8x cubed y to the seventh. And the derivative that's going to be 0 plus 24x squared y to the seventh. Oh, they're the same. And that's not always true. The mixed partials are not always the same. But I will tell you in this class, you can count on them always being the same. You have to be a really, really funky, weird function for them not to be the same. Like some weird, like piecewise function that someone has really tried hard to make it so this thing isn't true. So in general, you can be fairly confident in this class that the mixed partial with respect to y and x is the same as the mixed partial with respect to x and y. And then the very last thing I'll say is there's a notational issue with these mixed partials, and that if you write it this way, this means x first, y second. And if you write it this way, it means x first, y second. So they're backwards from each other depending on which notation you use. So just be a little careful there. If you see it written this way, just read from left to right. Do the derivative with respect to y first, then x second. But if someone has written it this way, you have to read from right to left. Y first, x second.